Because the afternoon time only solar is available. That's why he has demonstrated 3 MPPT algorithm with our solar setup. Okay, so real time solar system has used over there for getting the results and the demonstration. Now he will discuss about the pending portions of MPPT algorithms. Okay, and some simulation results he will demonstrate. Okay, Riju, am I audible?
Mm. Yes, sir. Yes, sir.
Your slide also visible from our end. Kindly carry on. Okay.
Okay, sir. Good evening, everyone. So I am Riju Nandi, a PhD scholar of NIT Rourkela under the supervision of Dr. Arnab Ghosh and Dr. Uh, Krishna Roy, sir. So uh, now I'm going to discuss of various incident MPP techniques of solar and wind energy system. Basically, I will discuss about the for the solar energy system MPPT technique. Also, I have discussed the P&O, the PSO, and the fuzzy. Uh, except this, I will tell about other the 3 and 4 method MPPT technique. Okay, so. Uh, so now I'm going to discuss about the incremental conductors. Okay. So, uh, like piano, this is also a classic MPPT technique. Okay. Sorry. Incremental conductors. This is the incremental conductors technique. Okay. In incremental conductance, we are sensing voltage and current simultaneously. Hence, the error due to change in indifference is eliminated. However, the cost and complexity of the implementation increases. Uh, then a P&O. For the P&O, it is a simple technique, also cost effective. But incremental conductance, it is cost and the complexity is high than P&O. The mathematical approach for calculating the position of MPP on the PV curve is given by P equals to V into I. All you know that power equals to V into I. So dP by dV equals to dP by dV PV equals to dVi by dV. At peak power point, dP by dV equals to 0. So I by V plus dP by dV equals to 0. This is the equation of the INC. Okay, if the operating point is to the right to the curve, you can see this is the PV curve. Okay, so this is the MPP point. This is the right side. This is the left side. So if it is the right to the curve, so dP by dV less than 0, then if I by V plus Ti by dV less than 0, that time V is decreased. If I by V plus Di by dV greater than 0, that time V is increased. Okay. If the operating point is to the left to the curve, then dP by dV greater than 0. Then if I by V plus Ti by dV greater than 0, that time V is increased, and I by V plus Ti by dV less than 0, that time V is decreased. Okay. This is the flow chart of the INC algorithm. This is the PV curve. So, uh, firstly, we have to read the voltage of PV voltage and current temperature and temperature. So next, so you can see that Di equals to IT into IT minus 1. So what is the Di means IT present value into IT minus 1 is the previous value, and dV equals to Vt minus Vt minus 1. Vt is the present value, T1 minus 1 represent the old value. Okay. Then dV equals to 0 means if this is 0, if true that Di equals to 0 is current changing the current equals to 0. If it is false, Di by dV equals to minus I by V. So if it is true, then go to the old value. If it is false, then Di by dV greater than minus I by V. Okay. that time maybe okay. If it is true, then go to the increase VT means increase VT is VT equals to VT plus del VT del dV. VT equals to VT plus uh, dV. Okay, and if it is false, it will decrease the VT. Then DI, if DI equals to 0, then false. DI less than DI greater than 0. Then it is if it is true, then increase VT. If it is false, decrease VT. After that, after the programming, after the function, after the programming, we got the PV voltage and current. So if we product the VNI, we'll get the maximum power point. Okay. So after MATLAB, I'll see after the theory part. I'll show the MATLAB. Okay, MATLAB is not doing part and whole part of the MATLAB means for the INC. So after the run the program, after run the program, run the MATLAB. Okay, I got the that value. Value means maximum for tripping value. For you can see for the VPV. This is the VPV. This is the IPV. This is the PV power. Means this is the PV power. That you can see that blue is the PV power and the green is the load power. Okay. From the 1,000 watt per meter square irradiance and 25-degree temperature is constant. Okay. For this, we got 206. For our specification, 206 is the maximum power. So I got the maximum power is 206. Okay. For the after the running the program, we got the 206. For 800, we got something 160 like that. For the 600, we got 120. Suppose like that, we got the maximum power. This is the load power also. This is the always load power is less than the PV power, small less than the PV power because of some losses. So some this is the load power following the PV power. Okay, this is the VPB and this is the IPP graph. So I'll show the MATLAB, but whole MATLAB, but if I'll run the program, it takes so much time. That's why I got the result and I have shown by PPT. Okay. So next is the variable step size P&O MPPT technique. Okay. I have discussed about the P&O MPPT technique. Now I am going next step on the variable step size P&O MPPT technique. The most commonly used MPPT algorithm is P&O. We know that. So due to its simplicity and implementation, it is basic form. However, it has some drawbacks like oscillation around the MPPT in steady state oscillation. You know that time P suppose decreasing, increasing, then got the maximum power. So oscillation always there. Slow response speed due to the change of the solar radiance. In most applications, the MPPT is achieved by connecting a power condition. Means converter means DC to DC, but DC to AC converter, anything like DC to DC like buck, boost, sepic, choke, any converter. Okay. So between the PV array and the load, to simplify the control system, the PV array operation point is employed to directly control the converter duty cycle based on the phase shift pulse with modulation technique. So for the variable step size technique, so dk equals to dk minus n del p by del I. Okay. So where n is the scaling factor, the performance of MPPT system and tuned the design process. So del p by del I greater than 0, the PV operating point at the left of the MPP. Okay. Del p plus del I equals to 0. Like that PRO technique, same like that, but del I equals to, there is there. when it is 0 equals to 0, that is PV operating point at MPP. When less than 0, that time operating point at the right of the MPP. This is the flowchart of the variable step size PNO algorithm. This is the measure VT and IT and calculate the power. Okay. After that, if it is PT del P greater than 0, so PT less than PT minus 1, so this is the old value, my present value greater than old value. If it is yes, then IT greater than IT minus 1. If it is no, so IT also greater than T minus 1. But if it is yes, this decrease the reference current. If it is no, increase the reference current. This is the opposite. Also, if it is yes, also increase the reference current. If it is decrease, then decrease the reference current. Here again, so if you know del P equals to PT T minus 1, del I equals to IT T minus 1. So we have calculate directly the calculator current and increment, also dk equals to dk minus n del P by del I. Okay. So like INC, we also got the so for the variable stress, we got the also yeah, for the 1800 watt per meter square irradiance, we got the maximum power. I have to see. We saw that we got the maximum power like 206. Okay, and load power is a follow the load power. So um, there is a must is a greater than the piano technique. That's why we have used now variable stress side piano technique. There's a VPP. I was saying the VPP and it's the IPV. Okay, for the 1800. Okay. Next, PSO. I have done the hardware also, but now I'll also fuzzy logic also theory part I have discussed, but we'll go the simulation result. So we got the simulation result like same like that. Okay. No, now we are coming. We're discussing about the adaptive neurophagy. This is the unfished technique. Okay. Uh, Sorry. Uh, you can see that there is this is the adaptive neuro interference system architecture. What is the adaptive unfished? This is the combination of ANN and fuzzy. Okay. Firstly, you have to in MATLAB. First, you have to uh, make a ANN. Okay, ANN file. For that ANN file, you have to put in the fuzzy. Okay. Uh, so fuzzy controller, you have to put some file in RR file, fish file. Okay, that is also one type of fish file. Okay, ANN fish file. That is unfish. Okay, so this is adaptive neurophagy. So there is a layer, two layer is there. Okay, like so if there's a layer 5 is there. Layer 1, layer 2, layer 4, layer 5 is there. Okay, so this is the input. This is the output. Okay, so you have you can see that this input power level is a over medium. This is a medium layer. Okay. So to demonstrate the unfished architecture, two fuzzy I, then the rule based on first order Stoichiometry model are considered as follows. So rule 1, if x is a1, okay, and y is b1, so then f1 equals to p1x by p1y plus r1. Okay. Rule 2 say if x is a2 and y is b2, then f2 equals to p2x plus p2y plus r2. Where x and y are the input. Okay, is the x or y in the input. Okay, and AIBI, uh, AIBI, this A and BI are the fuzzy variable. This is a fuzzy variable, and FI represent is FI means F1, F2 is represent the output with fuzzy sets. Okay, and PI Pi, Qi, and Ri are design parameters and are determined during the training process of unfit system. The output of the layer 1, this is the layer 1, so are the fuzzy membership pairs of the inputs where the given the following equation. So this is the equation O1 plus I. So mu AI x I where I equals to 1, 1 to 2, O1 comma I mu bi minus 2 u y equals to I equals to 3. So mu AI equals to 1 by 1 plus x minus ci by ai bi dash I equals to 1 is to 2. So layer 2, and it's in the layer 2. So O2 comma I equals to wi equals to u ai x star means into u bi y equals to I equals to 1 to 2. Layer 3 O2 2 comma I equals to wi bar equals to wi plus w1 plus w2 I equals to 1 comma 2. And layer 4 is 4 comma I. This is the wi fi, but wi pix plus qy plus ri, like that. Okay. So is the so after the for the unfees, the specification of for the specification for the maximum power is the 250 watt. Okay. But for other case, with the specification 206 watt. Okay. For the unfees based, I have designed for the 250 watt maximum power. That's why you can see that for the unfees, I got the PV power is a smoothly 250 watt, steady state 250 watt. You can see that it is tracked easily, smoothly in the PV power also, more smoothly than any technique. Also, because this is a ANN and fuzzy combined. That's why it takes. It is the also advantage of the any hybrid model. Okay, in the hybrid model, you got the maximum power smoothly. Okay, like you can see that PV power smoothly go to the 250, then steady state, then from the 800 go to the 200. Okay, then load power will follow uh, the graph. Okay, this is the VPV. The VPV is constant. Okay, for the IPV, this is for 100. This is some there, but 800 some fluctuation is there. Okay, so our theory part is complete. Now I can show the MATLAB. Yes. You can see that this is the INC MPPT. Okay, I have discussed about INC. Okay, INC. Okay, so for INC, I got this result. Okay, this is the MPPT. This is a MATLAB simulation of the INC. You can see that there's a variable variance has come. Okay, suppose 1000. This is the STR generator is there. Some time for 0 to 0 0.2, 0.4, 0.6, 0.8. Amplitude is 1, 0 0.8, 0 0.6, 0 0.4, 0 0.2 into 100, 1000. For this the ingredients changing, suppose 1000, 800, 600, 400, 200, like that will be changed. Then after the INC module, click the INC, you can see the programming INC post. Is the VF max at 300, VF at minimum 0, and VR initial is 210, and delta VRF is 1. So if ISMT is V old value is 0 and I old value is 0, and VRF old value is equals to VR initial, reference initial. So dv equals to v minus v old. I have told about this. The dv, what is the dv is present value minus old value. Okay, what is the di value? I value minus I old value. If dv equals to 0, okay, if dv equals to 0, so start if di equals to 0, v reference equals to v old value. V reference equals to v old value. If it is not, else if di greater than 0, that time v reference equals to vr old plus delta v reference. By the flowchart, I have designed this. I have discussed about the flowchart. You can also see that flowchart and going through the programming. Else v reference equals to vr old minus delta r end, and if di greater by dv equals to minus I by v, this is the main formula of INC. Okay, so v reference equals to v ref old reference old. Else if di by dv greater than minus I by v, that time v reference equals to v ref old minus delta v reference. Okay, and else v reference equals to vr old plus delta v reference. And if v reference, now last part is if v reference greater than equal to v rf max, the maximum value, or v reference less than equal to v minimum value, also both are similar. Now v reference equals to vr old. So end is the vrf old minus v reference, and v old equals to v, I equals to I. Okay. After programming part, we got the PWM. That PWM we have to give the gate pulse. After the gate pulse, we got the this is the PPP IPP. So we got the power. This is the power. We got the power. Okay, and this is the load power. You can see this is the load V I there. So product is load power. So this is the PV power load power. This is a scope. After the running, we got the PV power and the load power curve. Okay, and this is the PV power and the load power curve. You can see. Okay. So now this is the I now will go for VS variable step size piano. So you can see so for the piano technique, there's a two input is there, but for the variable step size piano, there's a 6 input is there. Okay, let's go to the function block. I'll show. Okay, you can see that function block decays to piano. Okay, DK, this is like anything you can name piano, anything. VSS piano. So there's a BK IK also input, I know, but there's AN, A1, A2, or DT max also there. So there's a D initial, a D minimum, D maximum is here. So D initial is a 0.42, a D minimum is 0.08, and D maximum 0.8. Okay. So that old value is 0, always 0. PK 1, 0, IK 0, DK always D initial. Anything D initial, suppose 0.2, 0.3, 0.4 initial, anything. So so calculate the P is VK into IK, and VP equals to DV, DI. You know about this. I have discussed what is the DP and DV. There's a AM equals to ABS DP by DV. If N less than DD max N, so that's why step 1 is N into M into A1 by IK. The step 2 is N into M into A2 by IK. Okay. So this is the if dp equals to 0 greater than 0 and dp equals to greater than 0, if di greater than 0, that means dk minus 1 minus step 1. Okay, we have to minus from this, and else dk minus 1 minus step 2. Okay. And if not if it is not, else it's not db equals to 0, not then di greater than 0, that time dk minus 1, then dk minus 1 plus step 1. Okay, else dk 1 plus step 2, like that. There is a minus, there is a plus. Else dv, if dv equals to 0, like that, di equals to 0, that time dk for first step, dk old value plus step 1, dk old value plus step 2. Okay. Similarly, like that for this part or for this part. Okay, like that. So it is the similar to the eins. Then last portion VK old value equals to present value, old value is present value, or the power old value equals to present value. Like this is the function. So this is the VSS technique. Okay. After the after the functional block, we got the DT ratio, the DT ratio. So we have used the PWM generator from the generate the duty ratio 0 to 1 value. Always you can see the duty ratio value 0 to 1, 0 to 1, 0 to 1, like the pulse it has provided. That pulse you have to give the gate pulse. After the giving the gate pulse, you got the PV power. This is the PV power you got. Also load power. After load power, you got the result. Suppose this is the I got the result. Okay. Yes, technique. Now go for fuzzy. Fuzzy technique. Yeah. So this is the fuzzy. Okay. Uh, for the now there is the one constant block I have been used, but sometime but I have been used also steer generator for 1800. You can see that all the MATLAB simulation I have been used only boost converter. Okay, for the boost converter, I got the maximum power. You can use also buck and Cepic also, converter, any converter also. But you can see for the uh, fudge control, if you go to that subsystem, there is a fuzzy. Okay, this is a fuzzy controller. Okay, this is the fuzzy controller. So this is the VPB IPB. Okay, there is a memory is there. They recall the memory. Okay, this is a product. Product means it is a mean product in the power. Yes, VPB IPB power. Okay. So this is the also product. Okay. And this is the DV. This is the add block. And this is the DP. This is also add block. Okay. This is a change in voltage and change in power. You can see that this power has come. Also, this power has come. This is the adding block is there to compare the DP. This is the DP means previous value is like present value. This is the present value minus previous value. Okay, this is the previous value, and after memory it will get the present value. Okay, similarly like that. Okay, yes, also DP1 is there. So there is a in fuzzy block. You can see that the fuzzy logic control is there. If you double click the fuzzy logic controller, this you can see that the fish file is PO MPPT fish file that I have been created. That I have been created that file. I've been created that file by using that. You can see fuzzy rule. Okay, fuzzy rule. You can firstly uh, you have to do like that for the input variable, for the two input variable, then output variable, nb, ns, jd, ts, pb. Okay, uh, like that you have to do in the MATLAB coding. If you go the if you go anything the like here, type fuzzy and enter. Okay. Right. Okay. After I think it will taking time. It will be taking time. That's why. Okay, I'll continue. Anyway, pathology design is come. So you can see that is the input and output is there. Have to do two input and one output. Okay. It take time. I think. Okay, like that, you have to do two input and there is a triangle, anything is a trapezoidal, triangle, Gauss, anything. But I have done for triangle only. Okay. So, like that, I have made the file. Okay, that I have made the file. After that, after that, the fuzzy. Uh, after that, I made the file. Then I recall I call that file is the in the fuzzy logic controller. Then after this uh, I got the duty ratio PWM. That PWM that PWM goes going to the gate pulse. After the gate pulse after the gate pulse I got the load power and the PV power. This is the load power and this is the BPB IPB. So this is also this is the load. This is the PV power. Okay. This is the PV power. This is the load power. After if I connected to one spoke connected to the BPP and load power, then I will get the result like that. Okay. This is the PV power. This is the load power. So next, I'll discuss about the unfis. Unfis. So uh, you can see this is the unfis. This is a big circuit because the hybrid module. You can see here is a irradiance and temperature is the input. Here is a all the technique. You can see that VPB IPP is the input, the function. Then we got the duty ratio, but there is a G and T, irradiance and temperature directly you have to give. Okay. Uh, then you got the duty ratio. Okay. Suppose in fuzzy logic controller, if go to the fuzzy logic controller, you can see there is a fizz file is there. Triple R. Uh, I say triple R dot fizz file. Okay, that fizz file is nothing but is the ANN. I made the ANN artificial neural network uh, block I have made that file. I put in the fuzzy logic controller. This is fuzzy and ANN. Then we both combined. It made the unfizz. So after the comparing, so there's a PID controller is there. After PID controller, it's generated duty ratio. The duty ratio directly goes to the gate bus, then generate the uh, duty ratio and get bus. Then we got the there's a three loading is there. Also you'll do for one load also, but I do for three resistance also parallel resistance. If any home appliance anything, there's a parallel resistance there. That's why I connected parallel resistance. Okay, so after uh, doing after getting the gate pulse, the boost converter generate the VPB IPB. Then there's a VPB. You can see the VPB is there, and this is the VPB load power, and also this is the VPB IPB. This is the P power, and this is the load power. Okay, so uh, from this circuit, okay, from this circuit after running, but uh, if I'll run the program now, it will take so much time because this is the this take so much time for the unfizz technique. unfreeze also. Any technique, it will take some taking time to run the program. So after running the program, we got that result. I got the result, the smooth result. I have discussed about it. Uh, how much I how much smooth I got the results. You can see 250, like smoothly I get the 250. Acha, already I told about that for the unfees. If you look at it, if you go to the PV array, I'll sh I'll show that why I'm talking the 250 watt. You can see that maximum power is 250 watt. There is a parallelistic one and series connected parallelistic one. Okay, if I connected the series connected is two, that time 500 maximum power 500 watt you get. But user defined I my session one and uh, 60 per module and open circuit voltage 37.3 like that. You can see. So that's why I got the value of maximum power 250 watt. Okay. So you can see that if I plot, okay, if I plot the graph, you can see that this is the maximum power. Okay. For the 1000 kilowatt per meter square means for 1000 kilowatt watt per meter square irradiance, you got the maximum power like 250. Okay, 250, 250, and for the 800, like the 200, for 600, 150, for 400 watt per meter square is 100, for 50, like for 200 watt per meter square, we got 50 kilowatts, 50 watt like that. Okay, this current is voltage is suppose 30.7. Okay, V2B is 30.7 and IPP is suppose 8.15. Okay, close. Okay, so after running the program, I got that margin. You can see that 30.7 like that. So we got like that 30.7 and current for this 8 point I told about suppose 8 point something. So that I 8 I got the 8 current. So that's why I got the uh, maximum power smooth and static and steady state PV power that. Okay. So I've discussed all about all the MPPT. Okay. Also hardware question, three MPPT for P&O, PSO, and Fuzzy. I have done hardware and software also, and so theory. But other things I have done only for MATLAB portion and theory portion. I have done many MPPT techniques like 20 to 25 techniques, but I will discuss about that 6 to 7 techniques. Okay. So now about the conclusion. So P&O and incremental conductance are the most popular technique due to their simplicity and relative good performance. And fuzzy logic and FIS and PSO provide excellent accuracy and adaptability, but at the cost of increased complexity and computation requirements. So thank you. Uh, uh, Thank you, everyone. Mm.
Thank you, Riju. So, any queries from the participants in?
Hello,
Hello.
good evening. I
Good
have
evening.
one query from this
Uh,
ANFIS controller that you have
okay.
used. In case of FIS, that means fuzzy logic controller, you are taking the input power and power of previous step like that for all of
Uh,
mostly all of the controllers. Why in this
yes.
case it is irradiance and temperature?
Uh, For the unfished any system, so you can see that that for the for the coding ANN, if you go for ANN part, ML part, okay, that time you have to data sheet is there. Okay, data sheet is there means there is a G and T. Suppose irradiance and temperature is there, and suppose BMP, IMP is there. You have to compare all the things. Okay, so when you do the programming anything, so that time only G and T value are there. Only that value is there. You have, that's why you have to take the input and G and T and got the VMP value and compare the VPP to VMP, like that. You have to got the P power and the load power.
That means you are trying to, that means taking the model of the PV system as a black box or gray box, and you are uh,
No, from
estimating
the
that.
from the PV panel, suppose in PV panel is there, okay, suppose sunlight is there.
Mm.
So when irradiance has come, that time you have to measure the sensor measurement, means irradiance sensor is there. Okay, you have to measure the irradiance sensor. Okay, and take it in Arduino anything. Okay, and temperature sensor also is there. You have to take also temperature continuously. Okay. For irradiance sensor, it will take you have to take irradiance as a by the sensor, and temperature you have to sense directly. You have to connect the sensor directly the Arduino. Then you go you will get the you'll get the VMP. So then after coding you'll get the VPP.
Okay. And one more question: how you have created this, shared this ANN and that FIS in this FIS? That means you are talking of ANFIS, Artificial Neuro Fuzzy Inference System.
Yes.
Still, Fuzzy Inference System FIS, fuzzy controller we have done.
Yes.
So I wanted to know more on that. That means how you have put this ANN in this fuzzy.
Acha. You can see.
Is there any such that means app available in MATLAB, or you have to create that? Like for if you
No. I have
type
created.
fuzzy, you go for FIS
No,
and
no,
create that.
I have created because it is, you can see, is it visible? You can see.
Yes.
You can see that fuse file is triple R dot fuse file is there. Okay. That triple R dot fuse file you have to create by NN. Go to the, suppose, go to the MATLAB, then search the NN start. Okay. NN start, then you, some block has come. NN block has come. Okay, that time input layer you have to decide, output layer. Okay,
Okay.
then you will after that you will you have to save that file in RRR file, RR fizz file. Okay, that RR file you have to give that fuzzy logic controller.
Okay.
Then you got the unfizz controller. This is a hybrid controller.
Okay. Thank you so much.
Thank you. Any
Okay,
question?
so any more queries? Is there any more queries? Okay, so I hope there is no more queries. Okay, so can we now we are going to conclude that session. Okay, so thank you Riju for delivering as well as demonstrating some hands-on as well as some simulations to in front of the participants. I hope a lot of person will get some beneficial inputs from your simulations as well as some experimental verifications. Okay, thank you all of you. So
Thank you, sir.
today we are going to conclude our sessions. Okay, this is a day